Here we have the composite function f of g of x, and we want to find the derivative of this composite function. And we want to show that the derivative of f of g of x is the derivative of f at g of x times the derivative of g at x. And this is called the chain rule for derivative. And the assumptions that are made here is that the function g is differentiable at x, and the function f is differentiable at g of x. And recall that the definition of derivative is of derivative of f at x is the limit of f of x plus delta x minus f of x dividing by delta x as delta x approaches 0. And then we also have the other form, which is called the alternative form of derivative. Is the derivative at a, at some number a, is the limit of f of x minus f of a dividing by x minus a as x approaches a. And again, we want to show that the derivative of f of g of x is the derivative of f at g of x times the derivative of g at x. And so first, let's call the composite function h of x. And we will use the alternative form of derivative to show that the derivative of f of g of x is the derivative of f times the derivative of g. And so we let h of x equal to f of g of x, then h of a. Then we need to show that the derivative of h at a will be the derivative of f at g of a times the derivative of g at a. And so the derivative of h at a, using this alternative form of derivative here, and then there's going to be f of g of x minus f of g of a dividing by x minus a as x approaches a. Here we just have the function f, then we just get f of x minus f of a. But here the function h is f g of x. And so in the place of f, we have to have f g of x, and in the place of f here, we have to have f g of a. And then next, we will multiply the top and the bottom by g of x minus g of a minus g of a. So we multiply the top and the bottom by the same thing, and so this is just 1. And so basically we're multiplying this quantity here by 1. And then next, we will rearrange things a little bit, and so we will put this under here, and then we'll put this under here. And then recall that limit of a product is just product of limits. This right here, this is just g of a, g prime of a, by the alternative form of derivative. And this is the limit of g of x minus g of a divided by x minus a as x approaches a. And so this, by this alternative form of derivative here, this is g prime of a. And then this is the same thing. Instead of x, now instead of a, we just have g of a. So this will be f prime of g of a. And so we have shown that the derivative of h at a is f prime of g of a times g of a. And therefore, so this is h of x right here. This is h of x. And this is called the chain rule or derivative. Now let's look at an example. And so for this function h right here, we can let g of x, and then sometime we call this u, g of x, equal to 3x plus 2. And then f of u, which is f of g of x, and is equal to u to the 4. And so the chain rule says that the derivative of h of x is going to be f prime of u times g prime of x. And so g prime of x, the derivative of g, or the derivative of u, which is the same as du over dx, and this is 3. So the derivative of u, or the derivative of g of x, is 3 plus 0, which is 3. And then next we want the derivative of f of u. Which is equal to this. F of u is u to the 4th, and so using the power rule, the derivative will be 4 times u to the 4 minus 1. That's the power rule. And this is 4 times u to the 3rd. And this is 4 times, but u is 3x plus 2. 3x plus 2 and to the 3rd. And so h prime of x which is equal to this. And it's going to be 4 and then times, and then g prime of x is 3. And so the final answer will be 12 times 3x plus 2 to the 3rd. And another way to find the derivative of h is this. We can multiply this out, but if we multiply this out, it's going to take some work to multiply this out. 3x plus 2 to the fourth means 3x plus 2 times itself 4 times. And we can multiply it out, and then we take the derivative, find the derivative, and we'll get the same answer. And so for large exponents, the chain rule is the fastest route to get to the derivative.